Okay, hello again for another CTF challenge. So this time we will solve the DeepDive CTF. So here we are given a memory image of a compromised machine and we are to analyze it and figure out the attack. So these are just 10 questions. We will be dealing mostly with Volatility tool, which is still the de facto standard when it comes to memory analysis. There's already a Volatility 3, but doesn't have enough useful plugins to analyze a compromised memory image compared to Volatility 2. Okay, so with that out of the way, let's start. First one, what profile should you use for this memory sample? So here, if you are not yet familiar with memory analysis using volatility, before you are able to really parse the contents of the memory, the processes running, and other stuff, you have to find out the exact OS version and build in order to really extract the information properly. And with that, the tool that we will use or the volatility plugin that we will use is what you call ImageInfo. So here running this, by the way, in order to run volatility, of course you have to download it. You have to follow the procedure that I shared on my earlier uploads. So you have to use bol.py space -f, then space the file, the memory image file, and then space the plugin. So in this case we will use ImageInfo, which is used to check the profile. As I said, the profile is the specific OS and architecture and build in order to parse the memory image content properly. Running this will take some time, so I have run it already, and as you can see here, it returned the below suggested profile, right? And for you to really know which profile is the correct one, you have to use that profile right here, for example, in the second example. And when you use another plugin here, for example, PSXView, it will properly parse the contents. If you use a wrong profile, it will show garbled output or not really properly aligned output like this one. So in this case, we have actually found the correct profile, which is Win7 SP1 x64 24,000. All right. So that will be an answer. Win7 x64 SP1. Okay, Win7 SP1 x64. Win7 SP1. And then 24,000. All right. Okay, for the number 2, what is the KTBG virtual address of the memory sample? So this one you could also find using the ImageInfo. Okay, so recall that we have run ImageInfo before. It also returned to you the KTBG address. Okay, this is the answer. Then next, fortunately, for the remaining questions, we can't really solve it using Volatility 3 because of the lack of plugins. So we will solve everything or the rest of the answers using Volatility 2. Alright, next question. Okay, there's a malicious process running, but it's hidden. So what's its name? So when finding a hidden process using volatility, this is a common technique used by malwares. They hide on the backward forward link. Let me show you. When you run volatility like this one, okay, let me just pull out the last command. The very basic command that you can run is pslist, or listing of the processes found inside that memory. Okay, this I'll give you a quick background on how to really analyze memory using volatility. So with the basics for now. So if you do pslist, you will be shown the forward backward link processes. Okay, these are the not hidden processes. So here it is, shown with the process name, the PID, parent ID, process parent ID, the threads, the handles, sessions, the start time, and the exit time. So if the process is hidden, it will not be shown when we enumerate the forward-backward link uh, using this pslist, or even using pscan. You cannot find it. So the plugin to use for that is the psx view of volatility 2. Okay, when we run it, it will show us the combined output of pslist, pscan, and the analysis which among the processes are hidden. Okay, it will take some time. Let's give it. Okay, I'll forward this. Okay, and now it's done. Actually, to scan for hidden process, you can just focus on the pslist and pscan result and find the ones with the false value. So in this case, one of them really stands out, which is this one. So it was not found using the pslist and in the pscan. So meaning it's really. Okay, number 4, what is the physical offset, the malicious process? So actually we have found it using the PSX view as well. So the very first column shows the offset. So this is the answer. Right, so we will be needing this offset in the succeeding questions. So let's go to the number 5. What is the full fat of the hidden executable? Okay, since it's hidden, so we can't really we can't use the PScan or the CMD line. It will not be found. So what we have to do is to use the bad info. So bad info can provide the offset address, copy, paste. Then we have to grep for that process. Grep s. Okay. Oh, sorry. BDS PS. And wait for it to load. And as you can see, we have found the path of the malware or the malicious process, and it's located in this is the logical or the device path. If we convert it to the path that we know, this becomes C colon space users run, which is this one. Okay, so next, which malware is this? So we found it as on Emotet. So what you can do is Remember, we have found the path here, so we could actually dump or extract the file and upload it to VirusTotal. Okay, so we need to dump the process. What we can do is use a proc dump. We'll create a directory first, dump, then I will use this command, uh, proc dump, and then directory will be the dump -- offset. This is the offset of the malicious process. Okay, then simply enter. Okay, and then what you can do is browse to that path. Okay, choose file. Okay, it's actually in the home downloads. Remember, we created the dump folder. This one. Okay, select it. Okay, and then there you go. Notice here we have a lot of hits showing it's detected as Emotet, for ESET, ANLAB, Polyonic, Malwarebytes, and so forth and so on. Okay, so number 7, the malicious process had 2 injected PEs in the memory. So what's the size in bytes of the bad that contains the largest injected PE? Okay, so we are to get the size of the largest injected executable. So we have found this. So when we talk of memory injection, the plugin that always comes to mind is Malfind. So we will again use the offset we found before. This time we will use the Malfind space -- offset, then the offset address of the malicious executable. Right? Then simply press enter, let it run. And notice here, it has found, oh, this process is the actual malicious executable. And then it found, oh yes, the injected process, there's one at this location. Okay, this is the address, then another one at this location, and then another one at this location, right? Okay. Okay, so based from the Malfind, we have found 2 injected process at this address and at this address. But in order for us to compute their size, let's find their VAD info using this command. VAD info -a. Then the first injected process is located here. Remember, this is the address. And then we'll give it the offset of the malicious executable, which we found earlier. Okay, this will give us the start and end virtual address here. Let's do the same for the other injected PE located here, 0x to A 80,000. Okay. Okay, this will give us again the start and end virtual address for the second injected executable. Okay, and then we have to use a hex calculator here. Simply subtract start from the end for both. You can use any hex calculator like this one. Okay. Right. For example, here, let's assume the second one. So simply copy here, copy the end. Okay. Copy the end and copy the start. Calculate the difference. Okay. Okay, calculate. Notice here, we get this result, which is actually the biggest of the two. And that's actually the answer here. I'll just need to append 0x again, because this is the semantics when writing memory addresses. Okay, next, this process was unlinked from the active process links list. Follow its forward link. Which process does it lead to? Answer with its name and extension. So we have found search indexer.exe. So as I was explaining earlier, 26. Let's go back. Notice. Oh, I have cleared it. So we can run the PS list. Okay, let's just PS list to show the forward link, backward link of the processes. And as we have found earlier, the we have found earlier in the PSX view. Okay, let me just pull it out again. Okay, just to save time, I have the screenshot. Okay, in the PSX view, recall this one, the PSX view. This one. Okay, so the process ID of the malicious executable is 2448, and when we run the PS list, notice here 2448 is nowhere to be found because it's hidden in the forward link. So we have to find the next process ID next to the 2448. So it's not actually in sequence because this is just showing the active processes. And the next number to 2448 is the 2616. Okay, which leads us to the search indexer.exe process. Okay, number 9 is what I believe the hardest question of them all. If you're not familiar with volatility, actually Volshell is quite an advanced utility within volatility. So what is the pull tag? So here we will use Volshell. Okay, this is how to use Volshell. So just the same syntax, and then use the plugin Volshell. And inside it, of course, you could do much more things like just assemble or show the e-process tree. Okay, if I'll show you help, these are the things to do with Volshell. Oh, okay. But anyways, the command that we are to use. Oh, okay. I'll just do it again. Okay. The command we are to use here is this one. So here we are to hold the pull header, and then we will provide the offset of the malicious process. Since this is the one being asked in the question, and the space address space or the base address space of that malicious process. Okay, and notice here we can get actually the pool tag, but in this case it's 0 because we have to understand the pool header concept, which can be found here. This is a very detailed website detailing the pool header. Notice here that we are just in the object header, and the pool header is actually here. So we have to move the address 30 bytes backward in order to get the pool tag info. But the thing is, we also need to know the size of the optional headers as well. So once we know the size of the optional header, we have to also subtract that to the address in order to direct to the actual pool header address. So hope that makes sense, but it will make sense here. If we have subtract 30, 0x30 here. Oh, sorry. We have to change this to object header. Yes, this one. Because we are pointing now to the object header, and we will subtract 30, the address. And here we will get an info mask of 8. So info mask corresponds to the optional header used. So here, this one 0x8. Okay, if I'll show you the website. Here, info mask tells you which of the optional headers, if any, are present. And since we got the 8, 0x8, it's actually using 32 bytes. Okay, and then that if we will combine all the info, so we actually need to subtract 30 bytes in order to get to the actual pool header address, right? So we do this again. Pool header, we actually need to subtract a total of 60 bytes, and that will give us the actual pool tag. So what we need to do here is convert this to decimal to hex converter. Okay. Okay. Then enter here, convert. But the thing is, we could actually convert this to hex to ASCII. Hex to ASCII. Okay. Actually convert that. But you have to remember that the ingenness of memory, it is actually data are stored in reverse. So if this is a hex, divide each bit into 2. We actually have to write it backwards, like 52306F, then 54. Okay, I actually reversed the previous one, this one. I've actually written it in reverse order, which became this one. Oh, sorry. Which became 5. Okay, let me try that again. So this will become 523006F 54. Okay, okay, that's how we write this in reverse. Then we convert them again, and that will actually give us the root or R0OT as the answer. Right? Then what is the physical address of the hidden executables full tag is actually shown in the command, which is this one. Uh, the physical address is 4 bytes plus the full header's address. So we just have to add 4 hex here in order to get the actual address. So here, okay, so we just need to add 4 hex, okay, then we can get this answer. Right, so that's how we have solved this. So hope you learned a lot.